Hello friends, today in this video we are going to discuss the topic Laplace transform. So we know that Laplace transform is having n number of applications in engineering fields. So in simple I can say we are using Laplace transform to solve the simultaneous linear differential equation as well as linear differential equation. In this topic we are going to discuss the following points. The first point is Laplace transform of some standard function. Second one is Laplace transform of multiplication by t factor, Laplace transform of division by t factor, Laplace transform of derivatives, Laplace transform of integration. To start with the topic, first we will see the definition of Laplace transform. So for that, let us consider f of t be a function for all positive values of t. Then Laplace transform is given by L of f of t. This L indicates Laplace transform. L of f of t is equal to integration 0 to infinity e to the power of minus st f of t into d. So this is the definition of Laplace transform. Here t and s are the parameters. So also we can say L of f of t is equal to f of s. Now I will take one simple example. Find the Laplace transform of, this is a shortcut way to express Laplace transform. Laplace transform of 1. So in this example, I am going to find Laplace transform of 1. So already I am having standard formula for this function, but I am here using the formula. By using the formula, I am going to find the Laplace transform of 1. So we know that solution. We know that L of f of t is equal to integration 0 to infinity e to the power of minus st f of t into d. So this is the definition of Laplace transform. So now I will put f of t equal to 1 because I am going to find here Laplace transform of 1. I will replace f of t by 1. So this implies integration 0 to infinity. So I will write this e raised to minus st as it is. Value of f of t is 1 into d. So this implies, we know that integration of e raised to ax is e raised to x upon e. That is, here e to the power of minus st upon minus s between the limit 0 to infinity. So that is Laplace transform of 1. So I will write here minus 1 upon s as it is. I will put here upper as well as lower limit. Upper limit is infinity. S into infinity becomes infinity. E to the power of minus infinity value is 0 minus the lower limit is 0. S into 0 is 0. Any number to the power 0 is 1. So this becomes 0 minus 1. Therefore, I will get here 1 upon s. Therefore, the value of Laplace transform of 1 is equal to 1 upon s. So now we will see Laplace transform of some standard function. So first I will write the formulas, then I will take examples based on the formulas. So already I have proved the first one is Laplace transform of 1, that is 1 upon s. The formula for L of 1 is 1 upon s. Similarly, I can prove Laplace transform of e to the power of at is equal to 1 upon s minus a. So here I can prove this one by using the definition. So I am writing the formula directly here. Laplace transform of e to the power of at is equal to 1 upon s minus a. Here a is the constant value. So I will take one example here. Laplace transform of e to the power of 2t. So if I get question like this, find L of e to the power of 2t. So I will apply the formula L of e to the power of 8. So by comparing this function with the standard function, I can see here the value of a is 2. So this becomes 1 upon s minus 2. This is the second formula. Similarly, I will take third formula, that is L of e to the power of minus 8. So this is 1 upon s plus 8. We can observe here, if it is e to the power of positive 80, here we are going to get s minus a. If it is e to the power of minus 80, then here we are going to get s plus a. So here also I will take one simple example. Find the Laplace transform of e to the power of minus 3. So I will compare this function with the standard function. So after comparing, I will get the value of a as 3. So the Laplace of this one is 1 upon s plus 3. The fourth formula, Laplace transform of sin a t. Laplace transform of sin a t. This equal to a upon s square plus a square. So this is the formula for Laplace transform of sin a t. Again here a is constant. So I will take example. Find Laplace transform of sin 4 into t. So I will compare this 4t sin 4t with the standard function at. After comparing, I can see here the value of a is equal to 4. So likewise, I will replace a by 4 in formula also. So I will get here 4 upon s square plus 4 square, which is equal to 4 upon s square plus 60. So you see next formula number 5, that is Laplace transform of cos a into t. So it is given by s upon s square plus a square. So this is the formula for cos a t. We can see here in case of sin a t, we have the formula a upon s square plus a square, where a is constant. In case of cos, the formula is like this, s upon s square plus a square. So I will take a simple example here. Laplace transform of cos 2 into t. The question is here, find the Laplace transform of cos 2 into t. So again I will compare this function with the standard function. So the value of a is here 2. So I will get answer as s upon s square plus 2 square, that is 4. So this is the formula number 5. Similarly, we have some more formula. Laplace transform of sine hyperbolic at. So this is the hyperbolic function, which is equal to a upon s square minus a square. So the next formula is Laplace transform of cos hyperbolic at. So it is given by s upon s square minus a square. So next formula is Laplace transform of c to the power of a, which is equal to 1 upon s minus a log c. So next, I will write some more formula. Laplace transform of t to the power of n, which is equal to n factorial upon s to the power n plus 1. So last one, Laplace transform of t to the power of n equal to gamma of n plus 1 upon s to the power n plus 1. So we can see here, these are the formulas for hyperbolic function. So you see here, Laplace transform of cos a t is given by s upon s square plus a square. That is formula number 5. And observe formula number 7. Laplace transform of cos hyperbolic a t is s upon s square minus a square. The difference is only in the sign. In case of cos trigonometric function, here in the denominator we are having positive sign. In case of hyperbolic function, in the denominator we are having negative sign. These are the difference. So formula number 9 and 10 are same. The formula number 9 is Laplace transform of t to the power of n, where n is any positive integer. If n is any positive integer, then the formula is like this: n factorial upon s to the power of n plus 1. If n is rational number, then the formula is gamma of n plus 1 upon s to the power n plus 1. So I will take one example here. Find Laplace transform of t cube. So t cube, I am going to apply the formula Laplace transform of t raised to n. So already I have told, if n is any positive integer, we are having formula like this: Laplace transform of t raised to n is equal to n factorial upon s to the power of n plus 1. This formula is for when n is any integer. So I will compare the function with the formula. Here, after comparing, I can see here the value of n is 3. So that is t cube is equal to 3 factorial upon s to the power 3 plus 1. That is 3 factorial is nothing but 6 upon s to the power of 4. So this is the Laplace transform of L of t cube. Similarly, I will take one more example here. Find Laplace transform of t raised to 3 by 2. See here, solution. So we can observe here, the power of t is not an integer, it is a rational number. So for that, I am going to apply the formula gamma of n plus 1 upon s to the power n plus 1. So this formula is useful when the power is a rational number. So this implies t to the power of 3 upon 2, which is equal to gamma of 3 upon 2 plus 1 divided by s to the power 3 upon 2 plus 1. So this implies gamma of 5 upon 2 divided by s to the power 5 upon 2. Now we see the linear property. So the first property is, if k is any constant, then Laplace of k into f of t is given by k into L of f of t. That is, while applying the Laplace, we are going to take the constant outside the Laplace sign. Similarly, the second property is, if k1 and k2 are two constant, then Laplace of k1 into f1 of t plus k2 into f2 of t is given by, first I will find Laplace of first function as well as Laplace of second function separately, that is Laplace of the first function plus or minus. If it is minus 10, then also this property is applicable, but this property is not applicable for division and multiplication. So Laplace of k1 into f1 of t plus Laplace of k2 into f2 of t. So already in first property we have seen, if k1 is the constant, write k1 outside the Laplace. So k1 into Laplace of f1 of t plus k2 into Laplace of f2 of t. Now we will take some examples. Find, first example, find the Laplace transform of t square plus a square. So find the Laplace transform of t square plus a square. Solution: Laplace transform of t square plus a square is equal to, I will apply a linear property. Here we are having two functions. So first, Laplace transform of the first function plus Laplace transform of the second function. L of t square plus L of a square. So L of t square, for this function I am going to apply the formula L of t raised to n, that is n factorial upon s to the power of n plus 1, because here the power is integer. So it becomes 2 factorial upon s is to 2 plus 1 plus here a square is constant. I will write a square outside the Laplace sign. So L of the remaining is L of 1. So this implies 2 factorial is 2 upon s cube plus a square. So we know that Laplace of 1 is 1 upon s. So we'll take one more example, that is example number 2. Find the Laplace transform of 2 into t raised to 3 plus cos 4t plus e to the power of minus 2t. Solution: L of 2t cube plus cos 4t plus e to the power of minus 2t. So this implies, again I will apply here linear property. So L of 2 into t cube plus L of cos 4t plus L of e to the power of minus 2 into t. So this implies, here 2 is constant. I will write outside the Laplace sign L of t cube plus L of cos 4t plus L of e to the power of minus 2 into t. So this implies 2 into, so here I will apply t raised to n formula. So after applying formula I will get 3 factorial upon s to the power of 3 plus 1, that is 4. So here I will apply Laplace of cos 80 formula. The formula is s upon a square plus a square. Here the value of a is 4, that is s upon s square plus 16. So at the end, here I will apply L of e to the power of minus 80 formula. The formula is s upon 1 upon s plus a. Here the value of a is 2. I will get 1 upon s plus. So this implies 3 factorial is nothing but 6. 6 into 2, 12 upon s to the power of 4 plus s upon s square plus 16 plus 1 upon s plus 2. This is the Laplace transform of this function. So we take last example. So that is Laplace transform of sin square 2t. So here the power of sin function is 2 and we have formula only for sin 80. So first I will apply multiple angle formula and convert this power to linear power. So first I will write the formula here. We know that cos 2 theta is equal to 1 minus 2 sin square theta. So this is the formula for cos 2 theta in terms of sin. Therefore 2 sin square theta, I will take this term to LHS and I will take cos 2 theta to RHS. This becomes 1 minus cos 2 theta. So therefore sin square theta is equal to 1 minus cos 2 theta divided by 2. So therefore sin square theta value is 1 minus cos 2 theta upon 2. But in example we are having 2t. So for that what I do here, I will replace t by 2t in angle. So I will get here sin square 2 theta. So I will replace here in angle t by 2 theta. Sorry, theta by 2 theta. So this becomes 1 minus cos 2 into 2 theta. So that is 4 theta upon 2. So this is the formula for sin square 2 theta is equal to 1 minus cos 4 theta upon 2. Therefore, I will simplify now the function. Laplace transform of sin square 2t is equal to 1 minus Laplace transform of 1 minus cos 4t upon 2. So this implies here 1 upon 2 is constant. I will write outside the Laplace transform. So the remaining is L of 1 minus cos 4t. So this implies I will write 1 upon 2 as it is. Now I will apply linear property here. Laplace transform of the first function minus Laplace transform of the second function. So this implies 1 upon 2 I will write as it is. We know that Laplace transform of 1 is 1 upon s minus Laplace transform of cos 4t is s upon s square plus 60. So this is the answer for Laplace transform of sin square 2t. So in this video we have seen the definition of Laplace transform, then formulas, some standard formulas, then linear property. After that we have solved some example. Thank you.